Hello everyone, I am Ajikumar, Assistant Professor Mechanical Department from Rohini College of Engineering and Technology. In this video, we are going to discuss about the subject Finite Element Analysis. The subject code is ME8692. So we are going to discuss some topics in Unit 2 of the Finite Element Analysis, and the Unit 2 topic is one-dimensional problems, and the syllabus coverage of Unit 2 is one-dimensional second-order equations, discretization, element types, linear and higher order elements, derivation of shape functions and stiffness matrices and force vectors, assembly of matrices, solution of problems from solid mechanics and heat transfer, longitudinal vibration frequencies and mode shapes, fourth order beam equation, transverse deflections and natural frequencies of beams. The course outcome of Unit 2 is, after successful completion of the program of Unit 2, the students can be able to apply the use of one-dimensional finite element equations. And the highest cognitive level given for this Unit 2 is K3 level, that is applying level. So first of all, we want to know the introduction to one-dimensional problems. The bar and the beam elements are considered as one-dimensional elements. These elements are often used to model truss and frame structures. A bar is a member which resists only axial loads, but beam can resist axial, lateral and twisting loads. Then we want to know the stress, strain, displacement and loading. In one-dimensional problem, stress, strain, displacement and loading depends only on the variable x, that is u is equal to u of x, that is displacement, and sigma is equal to sigma of x, that is stress, and E is equal to E of x, that is strain. And the stress-strain relationship is given by sigma is equal to capital E into E, and the capital E is Young's modulus and the small e is strain. The strain displacement relationship is given by E is equal to du by dx. Then the differential volume can be written as dV is equal to A into dx, that is A is area. And the types of loading acting on the body is body force, that is small f, and traction force, that is capital T, and the point load is capital P. Body force is a distributed force acting on every elemental volume of the body, and the traction force is a distributed force acting on the surface of the body, and the point load is a force acting at a particular point which causes displacement. And the finite element modeling, consists of the following, that is discretization of structure and numbering of nodes and elements. And the discretization of structure already we have discussed in the first unit in steps of finite element analysis. The first step of finite element analysis is discretization, the art of subdividing the parts into convenient number of smaller elements is known as discretization. And the second one is numbering of nodes. After the discretization process, this is the second step of finite element analysis in the first unit, that is numbering of nodes and elements. So this is a bar element. We are dividing this bar element into 5 elements, and the nodes are 6 nodes. And first, the shape function derivation of one-dimensional bar element. We want to consider a bar with element nodes and 1 and 2 as shown in figure. The U1 and U2 are the displacement at the respective nodes, and the U1 and U2 is the degrees of freedom of this bar element. Degrees of freedom is nothing but the displacement of this bar element at node 1 and node 2. Since the element has 2 degrees of freedom, so it will have 2 generalized coordinates. So we can form the equation as u is equal to a0 plus a1x. And a0 and a1 are the global coordinates. And writing the above equation in the matrix form, that is u is equal to matrix of 1 x and a0 a1, matrix of a0 a1. At node 1, u is equal to u1 and x is equal to 0, and node 2, u is equal to u2 and x is equal to 1. So when substituting this node 1 and node 2 boundary conditions in the above equation, we will get u1 as 0 and u2 is equal to a0 plus a1l. Arranging the matrix equation in matrix form, that is matrix of u1 and u2 is the degrees of freedom matrix, and the determinant of 1 0 1 and is the connectivity matrix, and the matrix of a0 and a1 as the generalized coordinates matrix. So this A0 and A1 we can write as 1 0 1 L inverse U1 U2, matrix of U1 U2, and we want to substitute the formula A11 A12 A21 A22, determinant of A11 A12 A21 A22 inverse is equal to 1 by A11 A22 minus A12 into A21 into matrix of A22 minus A12 minus A21 and A11. So we want to substitute this term in the above equation, and we will get the A0 A1 is equal to 1 by L and determinant of 1 0 minus 1 1 and matrix of U1 U2. So the A0 A1 values we want to substitute in the above equation. We will get U is equal to 1x and 1 by L, and the determinant of L0 minus 1 L and U1 and U2. So we want to use the matrix multiplication term 1 into 2 into 2 into 2, and we will cancel the terms 2 here, and we will get the answer as 1 into 2 matrix. So like this we can able to form this equation as U is equal to determinant of 1 minus x into divided by L comma x by L and U1 U2. So L minus x, 1 minus x by L is n1 and x by L is equal to n2. This is the shape function of this bar element, where shape function n1 is equal to L minus x by L and shape function n2 is equal to x by L. And next one is stiffness matrix and finite element equation of bar element. Same, we want to consider a bar element with nodes and 1 and 2, same like the shape function derivation, and U1 U2 are the displacement the respective nodes, and U1 and U2 is the degrees of freedom of this bar element. Same, we want to know the general stiffness matrix equation. K is equal to integral of B power T matrix of D matrix of B into dV. B is strain displacement matrix and D is stress strain relationship matrix. We know the shape function equation, that is displacement function U is equal to n1 U1 plus n2 U2. Shape function n1 is equal to 1 minus x by L and shape function n2 is equal to x by L. So it's a strain displacement matrix. We can write it as dn1 by dx and dn2 by dx, and we can find the answer as minus 1 by L and 1 by L comma 1 by L. So B transverse we get as minus 1 by L and 1 by L as a transverse equation. And the one dimensional problem, the stress strain relationship matrix D is equal to the Young's modulus. So K is equal to 0 to L minus 1 by L to 1 by L into Young's modulus E into minus 1 by L into 1 by L into dV. So when solving this equation, we can able to put dV is equal to A into dx and AE is equal to 1 by L square minus 1 by L square minus 1 by L square into 1 by L square into 0 to L dx. So integral of dx, we will get answer as x. So we can put the limit at 0 to L, and we will get the final answer by solving, and we will get the final answer is K is equal to AE by L 1 determinant of 1 minus 1 minus 1 1. So when we are finding the stiffness matrix equation, we can easily form the finite element equation of bar element. The finite element equation of bar element is, the general equation is F is equal to K into U. So we only two nodes are here. So F1 F2 is equal to AE by L matrix of 1 minus 1 minus 1 1, and the matrix of U1 U2 is the final answer for intelement equation of bar element. Hope you have a small idea finding about the shape function and stiffness matrix and finite element equation of bar element by watching this video. For any query, you can able to contact me in my WhatsApp number 8754 330058, and my mail ID is AJIKUMAR@gmail.com. Thanks for watching.